Okay, you give the call. Okay, everybody, next talk. I'm really interested into this talk because tomorrow I'm talking at WasmConf also about WebAssembly and SpinCube. So Danilo and Joe going to talk about virtual machine, container, and WebAssembly in some kind of face-off. So I'm really interested in this. So welcome.
Hey, everyone.
That was a little bit more enthusiastic.
Woo! Very nice. Testing the mic. Is the mic working?
Yes.
All right. Good afternoon, everyone. Before we begin, quick poll. Who remembers the first time you tried explaining Kubernetes to someone outside of tech?
Yes.
And maybe you got isn't this just the shipping container thing? Well, today we are going deeper into the magic world, virtualization, that powers Kubernetes to run virtual machines, containers, and even WebAssembly. Virtualization has come a long way from the days when we thought running multiple operating systems in one physical machine was magic. Today, we are going to explore this evolution from virtual machines to containers, all the way to WebAssembly, the new kid on the block. We'll see how this technology stack up in terms of resource utilization, portability, speed, and security. By the end, you will not only get to know how each one works, but have some ideas on where they shine. And we'll have a cool demo about Hyperlight, which is a library to create micro virtual machines really fast. No, ultra fast. And who knows, you might even pick up a few pointers for those next family explanations. My name's Joe, and I'm a software engineer at Microsoft Azure, and I am a proud maintainer of the CNCF Containerd Run WASI project. I'm also a maintainer of SpinCube and a recognized contributor to the Bytecode Alliance. And I co-organized the Systems and Programming Language Virtual Meetup, or SPLUM. And much of the content I will be presenting today is what I learned from attending this meetup. And you can reach out to all the socials I posted here. And here I have my co-presenter, Dan.
Yeah, hey everyone. I work in the same team with Joe at Microsoft Azure, working on open source. In particular, I'm a core maintainer of Hyperlight, the project that Joe just introduced about creating those micro VMs ultra fast. I'm also the author of Manning's server-side WebAssembly, a book that's currently in early preview. More on that later. And I'm also a big Star Trek fan, so if you have any Trekkies in the audience and you want to talk about non-tech later on, hit me up. And you can hit me up also in any of those socials there. And we have those at the end, too, if you want to take pictures.
All right. To understand where we are today, let's go back to where it all began. Virtualization is a technique to simulate physical hardware. And in the 1970s, virtualization advanced with the development of the so-called first-generation hypervisor, or virtual machine monitor, by IBM. So essentially, hypervisor has total control over the hardware it runs on, enabling it to manage and share hardware resources across multiple OSs. In 1973, Jared Popek and Robert Goldberg formally proposed 3 core principles for a hypervisor, and those are fidelity, safety, and performance. Fidelity says that any application runs on the hypervisor should behave like they are running on the physical machine. Safety says that the hypervisor should have the total control of the hardware instead of virtual machines. And the performance states that hypervisor should have a minimum overhead. They encapsulate these requirements with a famous criterion. For any conventional third-generation computer, a virtual machine monitor or hypervisor may be constructed if the set of sensitive instructions is a subset of the set of privileged instructions. And there we have many terms. So sensitive instructions basically refer to those instructions that modify the hardware. And privileged instruction refers to the instruction that will trap from the user mode into the kernel mode. So how is hypervisor being implemented? The answer lies in a technique called trap and emulate. In this approach, the hypervisor manages different types of instructions from the operating system. For non-privileged instructions, it basically allowed them to execute natively, naturally, introducing almost no overhead. For privileged instructions, however, the hypervisor will step in and trap them. And when these instructions are executed, the hypervisor emulates their execution, providing an illusion to the operating system that it's control of the physical hardware. So doing so, this ensures that even though multiple operating systems are running across the same hardware, but each believes it has exclusive access. Moving forward, in the 1990s, the personal computing dominates the market, and so the x86 ISA, or instruction set architecture, become dominant. x86 introduced the concept of protection ring, and basically ring 0 is the most privileged, and ring 3 is the least privileged. So application run on ring 3, while kernel runs on ring 0. However, virtualizing x86 is not easy, and it poses some challenges. And part of the reason is because some of the sensitive instructions are not privileged. Take the instruction popf as an example. It behaves differently in user mode versus in kernel mode. In kernel mode, it actually pops up the top of the stack and saves into the register. So it actually modified the hardware. But in the user mode, it doesn't. So in the user mode, it doesn't trap. And that's a problem, because if the hypervisor runs on ring 0 and virtual machine runs on ring 1, application runs on ring 3, that means this sensitive instruction that does modify the hardware does not trap to the hypervisor. And that means the hypervisor does not emulate this instruction. So this will cause security issues. And the first commercial company that tried to solve this problem is VMware. They introduced a groundbreaking technique called binary translation. Binary translation basically converts from one ISA to another. And in this case, it converts x86 and all of those sensitive instructions to a different set of instructions that does trap into the hypervisor. And so their commercial product called VMware Workstation fully virtualized x86, and that's why they have a huge market success. Around 2000, early 2000, like 2005, 2006, hardware companies like Intel and AMD introduced their own extensions to fully virtualize x86. And those are called VTX and AMDV. These extensions transform x86 virtualization by providing dedicated hardware support. And here's how it works. The CPU introduced new privilege level, and sometimes it's called VMX root. And in VMX root, the hypervisor runs in ring 0, and host application runs on ring 3. And there is a VMX non-root mode where the virtual machine and application run ring 0 and ring 3. So by extending the rings, and we also call it ring -1, we can run hypervisor in a more privileged mode so that it can trap those sensitive instructions, so that we can implement trap and emulate. Now I want to shift the focus to a totally different virtualization technique called containers. In the 2010s, container emerged as a totally different technology that fundamentally changed how applications are developed, deployed, and managed. In this era was driven by the popularity of the public cloud. The cloud demands have evolved with a focus on more consolidation, more density, and ease of software deployment and portability. And they think virtual machines are too heavyweight for their application usages. Recognizing the cloud demand for lighter, more portable, and resource-efficient solutions, they look into 3 kernel features from Linux: namespaces, C groups, and capabilities. And they basically combine these 3 features into a new name called Linux Container. So it was in 2008. So namespaces provide a view for each container or process to have its own view of the entire hardware. It has PIDs, file systems, and network. Control groups allow the host to define resource boundary for each container. And for additional security, Linux capability restrict the power of the root user within containers. So those privileged containers do not have full root access to the host systems. Later, tools like Docker built on this technology to create a container ecosystem that powers today's cloud-native infrastructure. And Docker really revolutionized to try to solve this problem of when you have 10 services on one side and 10 platforms on the other side, and how am I going to manage those combinations of services and platforms? And Docker came in and said, we have a standardized package format and a standardized operations. So with Linux container providing a lightweight, efficient solution, the cloud now has two main options for virtualization: virtual machines and containers. While both technology offer isolation and resource sharing, they do so in very different ways. Virtual machines require full operating systems, while container only share the operating system kernels. And virtual machines offer strong isolation, but containers, because they share the same kernels, they share the kernel vulnerabilities, so they have a bigger attack surface. And now, with that said, I want to shift to a totally different virtualization technique called WebAssembly, and then I will hand it off to Dan.
All right, so understanding where we came from with VMs and containers, let's tackle the new kid on the block, WebAssembly. And I think a fair first question here, what is WebAssembly? And I always like to correlate it back to what we do know, like x86, 64, architectures that we're familiar with, R64, because in the same way that you can compile your code to these architectures, like x86, 64, you can compile your code to WebAssembly. So maybe that's our answer. WebAssembly is a compiler target. Awesome. But we can drive that comparison a little bit further. So say for x86, 64, R64, you can walk into a store and be like, hey, I want a computer running on this chip, on the x86, 64 architecture. But if you try to do that for WASM, be like, hey, I want a WASM computer, you're probably going to get weird looks. So you cannot do that. And that is because WebAssembly abstracts over this hardware. So x86, 64, R64, whatever. So it is, aside from a compiler target, a hardware abstraction layer, or HAL. And it is a HAL built with a couple core principles in mind. First one is for it to be fast. And by fast here, we mean sort of predictable, near-native performance. We want it to be safe, meaning it was designed to run within a sandbox environment. Initially, when WebAssembly came out, it was designed sort of for the browser. So in that scenario, we wanted to run within the V8 engine securely. But right now, running it on the server side, that can be just a standalone WASM engine. Some people might be familiar with, like WASM Time, say WASM Edge, whatever. Also wanted to be hardware independent. I mean, that's a given one, right? A hardware abstraction layer. And this is sort of building in the sort of giants like Java, Java bytecode, the write once, run anywhere idea. Although, differently from Java, we wanted WebAssembly to be language independent. And so Java bytecode, you compile Java or sort of similar languages like Kotlin and so on. Meanwhile, WebAssembly, right now, I think we have 40 plus languages that compile to it. So sort of a bigger scale there. But that's not all. That's sort of WebAssembly in 2017. WebAssembly today is quite a bit more. And that's due to the introduction of something called WebAssembly components. So perhaps a better question is, what is WebAssembly today, right? What are these WebAssembly components? So to clarify, this back in 2017, WebAssembly was introduced with 4 basic types. And these were 2 integer types and 2 float types. And if you wanted anything higher level, you had to build atop of these types, also leveraging the linear memory. Meanwhile, WebAssembly today with WASM components, out of the box, you have access to higher level types. And that's through a canonical API that establishes how to lift and lower from those types through code generation. And what that gives you is that it gives you true language independence and agnosticity. So say in this example, we have a machine learning library written in Python, say your app written in JavaScript. You can build those two into WebAssembly binaries and then compose those together into a single WebAssembly binary. So you can have those two interact seamlessly, like different languages with different memory managements through, say, function calls. So now we understand VMs, we understand containers, we understand WebAssembly. When do we use each one of these technologies? How do they differ? And this is the real meat and potatoes of this talk. This will be comparing we'll be comparing them in a couple categories. And by the way, huge credit to Alex Crichton here. A bunch of these slides were based on content that he has put out, one of the core maintainers of WasmTime. So yeah, just wanted to shout that out. Thank you, Alex, if you're watching. And anyway, so back to it. The categories that we will be comparing are 1, security, 2, speed, 3, resources required, 4, cold start. So that's another facet of security, or not security, speed, portability, and cross-guest communication. If all those are unclear, I'll clarify them in a little bit. Okay, so starting off with security. On one side of the ring, we have VMs and containers, battle tested for years and years, and you can trust the isolation that they provide. On the other side, you have WebAssembly, which is a formally proven sound language, and we even have some sandboxes that are mathematically verified to be safe. So at least from our standpoint, we think that those two compare quite a bit. Just depends, WebAssembly being the new kid on the block, you're sort of right to be skeptical, but we'll call it a draw. And that is until you introduce humans, sort of like human error. Because, WebAssembly engines, even though there are some that are mathematically proven to be safe, in reality, production engines, they're not going to be bug-free, right? So you can still have errors that could lead to exploits in the same way that with VMs and containers, even though they're hardened by all the years that they have, you can still have exploits due to the complexity of hypervisors that Joe introduced. And by the way, I just want to give a shameless plug to my talk from WasmCon of last year called Sandboxing Your Sandbox, Leveraging Hypervisors for WebAssembly Security. In there, I talk about sort of security and layers to account for that human error that we have on how you can use sort of all these technologies together. Okay, next up, speed. Speed is where sort of VMs and containers have a huge leg up. And that's because you have a full OS and you're running at sort of unrestricted access there with multiple processes, and you're running at native speed. Meanwhile, WebAssembly, that was never a goal. You'd want to run at near native speed, which usually means about 20% overhead. Next up, resources required. So we had a draw, we had a win, but resources required is one where WebAssembly really shines. And that's because, again, VMs, containers, they're big, right? So you have a full OS, and you are in the scale of gigabytes. So say you have a service with like 10 VMs, you could probably replace that if you, say, transition to WebAssembly with 10,000 instances of WebAssembly, which of course is a little bit of an unfair comparison because with VMs you have, like, again, a full OS, while WebAssembly you're dealing more at like the level of an executable. But still, if that's a trade-off that you can consider, that's something to keep in mind. Now, cold start. Again, sort of like speed. However, in this one, WebAssembly comes out on top. And that, again, another reason, maybe you call it a feature of VMs, because they are so big, there's a lot to set up. There's a lot to spin up, processes and so forth. Meanwhile, with WebAssembly, it was designed for the browser, and it was designed with streaming compilation in mind. And what that means is that, so say a scenario, you're visiting a web page, that web page pulls in a WASM module. We wanted, or design and spec, designing WebAssembly, for it to be able to be downloaded or compiled quicker than it is downloaded. So as soon as you finish downloading, you're able to hit the ground running and have it executing. Next up, portability. This WebAssembly comes out on top, and that's because it is architecture independent, while VMs and containers, they're per architecture. So with containers, you might be stuck having to create multi-arch images, while with WebAssembly, that's just a non-issue. Next up, cross-guest communication. So what I'm talking about here, to clarify, is how does container A talk to container B? And with containers and VMs, that's usually, you rely on things like Kubernetes, sidecars, serializing protobufs. While with WebAssembly, with the introduction of WebAssembly components, we have a great story here. And that's because if you remember that example that I had in the beginning with the Python and JavaScript, you compile those two, you get them in a single executable. And then communication between those two sort of like microservices almost, they behave like inter-process communication. So those are essentially function calls at the end. So, and that compare that to, say, VMs and containers where you have like a network stack, right, two microservices interacting. You don't have that overhead of serialization, like JSON or anything network related with WebAssembly. Okay, time for our Hyperlight demo. And this here, we want to sort of try and bring it all together, you know, using the best of VMs and containers and WebAssembly all together. And I'll stop, I guess, speaking in a little while, but just a quick 101 on Hyperlight. Again, it is a library that lets you leverage hypervisors to create these OS-less, so no OS, micro VMs very quickly. And we're talking very quickly, sort of spans of like 1 to 2 milliseconds. To run untrusted code safely. Very quick intro, but if you're interested to learn more, this is the blog post that we put out literally 3 days ago on Hyperlight, as was our announcement coming open source. So if you want to learn more, see some examples, that's a great place to look at. Okay, so in this demo, we'll be looking at two main applications. The first one is demo guest, and hopefully you can read it. But the first one, that's a demo guest, and that's an x86 64 unknown none native Hyperlight guest. So that's essentially the malicious code that we're trying to execute, sort of simulate it, right? And that will be running inside of demo main. That is an HTTP server that's leveraging Hyperlight's SDK, so to create those micro VMs. Oh, and by the way, the demo guest, this is running a native binary, but we can also run WebAssembly. I won't be displaying that here in this demo, but if you want to learn more about it, feel free to reach out to me after this talk, and I'll tell you more about it. Okay, so demo guest, I told you Hyperlight executes arbitrary code safely, quickly. And we do that by spinning up a micro VM that has no OS that executes functions. So we're at that function granular level. So demo guest in particular exports two functions, or we call them guest functions. And the functions are print output, which you can probably guess, print to standard output, and dereference raw no pointer. And this is to sort of simulate, something that someone might be trying to do that's malicious to sort of crash your process. Oh, something else I want to point out here is that print output, we're running in OS-less VMs, so you don't have syscalls. And to do something like printing to standard output, you escape the VM to do something that we call a host function call. So those sort of similar to syscalls. So you exit the VM, make that host function call, you return then to the VM, and then yield. And then demo main looks somewhat like this. We have two parent routes. One is Hyperlight, the other one is no VM. In the Hyperlight and the no VM, we have two mirrored routes. That's the hello world. In Hyperlight, the hello world route will be calling that print output guest function. And the no VM one, it will just be doing essentially the same thing that the host function in the Hyperlight example would do. So essentially a print line statement. For the Hyperlight one, we have two options. We have a warm endpoint and we have a cold endpoint. Cold will spin up a new micro VM on every request, and warm will pull from a pool of pre-instantiated sandboxes. And then safety, deref raw no pointer, that's just an endpoint to call that other guest function. And VM count is another endpoint to check the number of live VMs that we have. And I wanted to add that in particularly because the deref raw no pointer will execute in a warm Hyperlight VM. So say if it did crash and something went wrong, malicious, right? The VM will no longer be alive, but we can check if it's live with the VM count. Okay, demo time. Right here, I'll try and mirror my display. All right, perfect. So on the side there, you can see that we have demo main running, and I have a couple of pre-instantiated sandboxes. And you can see that we're listening at that port 3030. And then here, I have a couple of requests that we'll make to see it in action. So we'll start off with sort of like a tame one, just a no VM route, just a hello world. And all this does is it makes a print line, hello world, I'm not executing inside of a VM on the server side. And in here, we get just an output saying function called outside Hyperlight VM. Not too exciting, but now we can have it in Hyperlight. And this is the cold example, by the way. So we get guest function called inside a cold Hyperlight VM. And on the server side, or our demo main side, we have now a green message with a smiley face saying that we're executing inside of a VM. For completion, I can show you the warm example as well. And I mean, visually, they're indistinguishable, but we'll look at some benchmarks later so we can compare the two. I showed you that we had a couple of sandboxes pre-instantiated, so we can check the VM count. And you see we have 10 VMs pre-instantiated. That's what that warm one is pulling from. Now that we saw the VM count, let's check out that deref raw null pointer call. You see we get some error logs. And in here, we see unexpected VM exit, unexpected KVM shutdown. Probably improve the error message a little bit for this example. But the idea there is that now, if we call that VM count again, we're still at 10 VMs. And this is because in between each of those guest function calls, we're resetting memory. And so they're isolated, and it all works fine still, even with something that could potentially crash the process. Now, let's try and running some benchmarks. And here, hopefully you can see, but I'm running Hey. This will just do some benchmarking. We'll run like 200 requests, and it will monitor the time that it takes for the response time there. So running that, and I'm running the cold one first. See a bunch of print lines. And here, we see that we got an average response time of around 100 microseconds. So what is this, right? What we're doing there is we're calling the cold endpoint. We're creating a new sandbox. After creating the new sandbox, we're calling print output. Print output will then call into the host. So we'll do a VM exit. Then we'll do the print line. We'll then, after the print line, we'll yield back to the guest. The guest will then just return, yield back to the host, and that's the completed operation, and that took 100 milliseconds. Now let's try the warm one. Let's see how that looks like in comparison. Now I ran the warm one, and we can see the histogram looks a little bit weird, and we got about 55 milliseconds response time. But let's just check out our VM count. If we do that, we see that we're at 48 VMs. So not all of those requests were really warm, because we had to create a couple of VMs, so we have no resource contention. Let's try running warm again. Now we see we get more of a normal distribution, and we're running at an average 12 millisecond response time to do all that. Cool, now let's hit our program with some real payload, 1,000 requests with a concurrency of 5, and we're running that cold endpoint. Now with a bigger sample size, we'll see we're running the cold endpoint, so creating all those VMs and executing that function call with multiple VM exits in 13 milliseconds, which now you can guess warm will look even better. And if you run warm, we called into a VM in 1.4 milliseconds. Now just for fun, we can compare it to our original hello world that has no VM, just a normal function call. And what that looks like is 1.9 milliseconds. So we managed to call into a VM and do that all quicker than we did with a normal function call. Obviously, there's some variability here, but pretty cool. OK, so we're at 5-minute mark. I want to transition back in here to show you the key takeaways. Joe mentioned those family dinners, people asking, what do you work with? So if you want to talk to them about this talk, you can give them these key takeaways. And the key takeaways that we want to highlight is 1, WebAssembly, born as a compiler target that is a hardware abstraction layer. WASM today, with the WebAssembly components that I introduced, standardizes the communication between components in a way that resembles that inter-process communication, right? Those function calls without a network stack or serialization. And now if you want to decide, maybe your project, do I use VMs, containers, do I use WebAssembly? That's the bullet point that you want to look at, the third bullet point. VMs and containers are awesome when you want something that has been sort of battle tested, for years, and you want to be confident and maybe tell your boss like, hey, this is good, and that provides you native speeds. Meanwhile, WebAssembly is awesome when you don't want cold starts, you want that fast cross-guest communication, again, those function calls, great portability, and resource efficiency. A couple of applications there that you can think of, maybe serverless, edge, IoT. Those are places where WebAssembly really shines. And then finally, we finish off with the Hyperlight demo. And I showed you how you sort of can create those micro VMs in 1 to 2 milliseconds to run your untrusted code safely. Now, I want to just do a final shameless plug. and that is to my book, Server-Side WebAssembly. We're currently in early preview, and Manning gave me a QR code to give out in this talk with 45% off with that code. So if anyone is interested and wants to take a picture and check out the book, maybe you like my introduction to WebAssembly, this is the time to do so.
I mean, you could bring it for everybody for free.
I mean, it is still currently an ebook, and there's 4 chapters out, so I can't give it out. But I will get 25 copies free potentially next year. So maybe next Cloud Native Rejects, I'll be here with a couple of book copies. Okay, so now finally, to finish off, I want to ask if we have any questions, and if you want to check out on our socials, those are the links back again. Thank you.
Any questions? Okay. I go first up.
So just so in a Kubernetes world, how does this really look like? Do you just build your application? You put in a registry? How does all that work as well?
So what specifically are you referring to? Hyperlight? How does it work in the Kubernetes world?
Well,
WebAssembly?
Yeah, well, all of it, really.
Okay, so WebAssembly, do you want to take the WebAssembly one? You're more involved with CI work?
Yeah, so you specifically ask her about like registry. And tomorrow, WasmCon, there is a talk about like how do you package Wasm as an OCI package. So the short answer to that is now Wasm components can be packaged as OCI artifact. And you can use the similar way how you deploy your containers, upload them to registry, the same way you do to the Wasm components as OCI artifacts. And with projects like Run WASI, you can directly pull from the OCI registry and get a component down, unpack them to your local file system, and orchestrate with Kubernetes. So everything here will work with the existing systems.
And as for Hyperlight, you can use it as a normal library, so you can embed it into your application and just sort of deploy like you would with a normal container to run those micro VMs. And I have a couple of other demos that'll probably be displaying around the weekend in KubeCon, so if you want to catch me, I have like running Flatcar and those things. Maybe we can spin up some orchestration there.
I'm also shameless plugging now. Tomorrow at WasmCon, I've also a talk about SpinCube, and this gives you also the glue for Wasm and Kubernetes. Very interesting. Okay, pass to you.
Actually, what's interesting, though, the way you describe deploying or using Wasm to deploy on Kubernetes, it's essentially replacing containers. I don't think many people say that. Actually, the question I wanted to ask was, do you agree with that? I wanted to see if you agreed. And the second question I wanted to ask was, when you're running Azure now, it's already, for serverless, it's already using Wasm a lot. You don't care really as a user. That's my take. So can you describe, is that true? I mean, to what extent now is Azure using WebAssembly underneath the hood, so to speak?
Yeah, so to your first question, do I agree Wasm is gonna replace containers? Well, there are people saying, Wasm is becoming the third wave of compute. The first wave being virtual machines, the second wave being containers, and the third wave being Wasm. And I think the implication here is Wasm is gonna be an extension to even greater areas, like applications like Azure, edge computes, IoT devices. Those are the use cases where Wasm really shines. And in traditional long process workloads, virtual machines and containers shine over there. So they have trade-offs. But I do think Wasm is becoming an alternative to containers, just like containers are being alternative to virtual machines. But they are not going to replace the prior technology. And to your second question, is Azure running Wasm right now? Well, Dan can talk about his work on the Hyperlight, but there is an Azure AKS WASI notebook and cluster, and you can install that extension, and that will give you a cluster with built-in, the Spin sham, and that will execute Wasm workloads in AKS.
Yeah, on the Hyperlight side of things, I think last year's Microsoft Ignite presentation, Mark Rusinovich gave a talk introducing Hyperlight and mentioned how, Microsoft is a public cloud, we cannot just run WASM raw. And one alternative to that is running it within the hypervisor isolation that Hyperlight gives you. So, running WASM within Hyperlight, and we definitely have a couple of, I guess, services that are going to be based on that. Yeah.
Can you just help me understand the positioning of Hyperlight in relation to something like Kata containers and gvisor and that sort of thing?
Yeah, so it's a little bit different. A lot of people often compare it with Firecracker, but they're different really in the sense that Hyperlight is meant to be used as something embeddable. So say you have your application, you wanna say write a plugin, right, to run untrusted code. You can then leverage Hyperlight within your own application to spin up that OS-less micro VM. So that's one side of thing. The other aspect is really, I guess, the application of it as is right now, because we are OS-less. And so whatever syscalls you want to have, whatever higher functionality you want to have, you most probably will have to define those as host function calls. So you're a little bit more restricted on what you can do for the exchange of that performance and that we saw.
Cool, thanks.
Yeah.
Okay, then thanks again, and yeah, last talk for today.
Yeah, thanks for having us.